Okay, so we've talked about how to find the sum of the terms of an arithmetic sequence and the sum of the terms of just any kind of, generic sequence and summation notation. And we know, of course, that the sum of the terms of a sequence, that's called a series. So now we move on to geometric series, which is the sum of the terms of a geometric sequence. So if we want to find the finite sum for the terms of a geometric sequence, we're going to use this formula. Okay? Now, this formula, I'm not going to derive it for you. It does work only when r is not 0 or 1. That's because a geometric sequence can't have an r value of 0. And if r happens to be 1, then that denominator right there is going to be 0, so it's not going to be defined. All right, so let's just put this formula into place, or into play here. Let's find the sum of the first 15 terms of a geometric sequence where the first term is 4 and the common ratio is 3. Now this n right here represents how many terms you're adding up. So when we say the sum of the first n terms, that's what the n represents, and it's the same n right here. Just like these r's are the same r's, that common ratio for that geometric sequence. All right, so it looks pretty easy, right? We're just going to plug in 15 for n. We're going to plug in 4 for a sub 1. We're going to plug in 3 for these r's. So it really is just a matter of plug and chug. You want to be really careful with this. You want to make sure that 15 is on that 3 and not on the outside of those parentheses. That's a common mistake that I see. But you can put this in your calculator, and that's the number you should get. You should pause the video, go grab your calculator, and make sure you can get this same number. And if you can't, let me know. Like take a picture of your calculator screen or something and send it to me, and I can help you figure out where you might be typing stuff in wrong. All right, now, in this formula, because this formula is for a finite sum, if the r value happens to fall between -1 and 1, okay, if it happens to be any of those numbers between -1 and 1 on the number line, then this r to the nth power is going to go to 0 as n goes to infinity. Now what that means is that if r is something like, say, 1/2, then this r to the nth power, if we have like this 1/2 to the nth power, as n gets bigger and bigger and bigger, so think of 1/2 squared, 1/2 cubed, 1/2 to the 4th power, 1/2 to the 50th power, that is going to go to 0 as n gets bigger and bigger and bigger. So what that does for us is it gives us a formula that we can use for an infinite sum. So we've got that finite sum formula here. If my r value happens to fall between -1 and 1, I can use this formula for an infinite sum. That means I can actually take the sum of an infinite number of terms for a geometric series. Now, this is also sometimes abbreviated by saying the absolute value of r is less than 1. So that's an absolute value inequality. These two mean the same thing. I just figured that maybe if I wrote it like this, that might be a little too confusing because most people aren't really familiar with absolute value inequalities. So I chose to write it in this compound inequality form there. All right, so let's see how it works. This infinite sum is actually pretty darn cool. All right, so let's find the infinite sum. Now, how do we know it's an infinite sum? Well, 2 ways. 1, I told you. And 2, see that dot, dot, dot there? Keeps going. So it's an infinite series, so we got an infinite sum. To use the formula that a sub 1 over 1 minus r, I'm going to need the first term, and I'm going to need the common ratio. The first term is 1/2. That's easy, right? It's just right there, first term. The common ratio is the number you have to consistently multiply by to get the next term. You can also get this common ratio by dividing any term by the one right before it. So this 1/2 you can just get from what we call inspection, where you can just say, hey, what do I have to multiply this by to get this? What do I have to multiply this by to get this? Or you might have to do some computations. You take any term, let's grab another in here. You take any term, let's take 1/4, and divide it by the one right before it. And you're going to get 1/2. Let's say you took 1/16. Okay, so you take 1/16, divide it by the term immediately before it. Guess what you're going to get? Oh yeah, 1/2. So if it's not obvious to you what that common ratio is, you can always find it by dividing a term by the one right before it. Now it's just a plug and chug. So we get 1/2 over 1 minus 1/2, which is 1. That's really, really strange for some people. This means if you add a 1/2 plus a 1/4 plus an 1/8 plus a 1/16 forever, a lot of people think, well, if you're adding stuff forever, then this is going to be an infinite number. Not necessarily. So this does just add up to 1. So let me show you visually what's happening here. So if I just start off with, say, a square, that's one thing, right? If I split it into 2 pieces, that fraction right there is half of what I originally started with, right? So this right here, this whole thing is my 1. That's a 1/2. If I take this piece over here, also a 1/2 by the way, and I split it into 2 pieces, this piece right here is a 1/4 of the original. If I take this piece and I split it into 2 equal pieces, that's an 1/8 of the original. Okay, if I split this one, that's a 1/16. Split that in 2 pieces, that's 1/32. So you can kind of see where this is headed, right? So what I'm doing is filling in this whole thing. Remember this square here is 1. So I'm filling in this with using those little infinite parts. All these little infinitely small pieces are just slowly filling in that whole box. All right, so let's look at another one here. So let's find the infinite sum. Ooh, that's crooked. Of this series. All right, it's pretty obvious that this is the first term because it's the first one. It's an infinite sum because it says here and because of the ... So if it ends with ... now just because it has a ... doesn't make it infinite. If there's something after this, then the ... the ellipses here are just showing you that that pattern continues until that ending point there. But because it ends with that, it means we are going to continue on forever. So we get a first term of 0.9. Now where did I get that R value of 0.1? Just like before, you can take any term and divide it by the one right before it. All right, so I just take any term, let's take 0.09. and divide that by the one right before it, which was 0.9, and I get 0.1. If I did 0.009 and I divided by the term right before it, which is 0.09, again, I get 0.1. Now, don't just divide any 2 terms in any order. It's always a term divided by the one right before it. Now that we have these 2 things, we've got our infinite geometric series formula. We plug it in, we get 1. The answer is not always 1, just in case you're wondering. But let's look at this. This one's really interesting. If I were to add 0.9, let's see. If I take 0.9, 0.09, 0.009, 0.0009, so I'm just lining up those place values. Look what I'm going to get. So you can kind of see how these place values are going to line up. I'm going to get 0.9, 9 and a bunch of zeros, 9, a bunch of zeros, 9, a bunch of zeros, and it's just going to keep going. So this sum is going to add up to be 0.9999999 repeating forever. That means that 0.9 repeating forever is exactly the same thing as 1. Alright, so listen to me again. I'm not saying it's approximately equal to. I'm saying that 0.9 repeating forever is exactly equal to 1. Not approximately, doesn't round to be that. These are exactly the same number. Now, if you stop putting that dot, 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 no, that's not equal. This is not equal to 1. It's this 0.9 forever that's equal to 1. Let me just show you another way of thinking about that. We know that 1/3 is 0.3 repeating forever. Well, 2/3 is 0.6 repeating forever. So it stands to reason that 3/3, right? 369 would be 0.9 repeating forever. 3/3 is the same thing as 1. Pretty cool, huh? All right, you had to go get a drink, right? I hit record and suddenly you become the thirstiest beagle in all the land. All right, so let's see here. We're going to find the infinite sum. We can tell what the first term is. It's just 2. We have to find that common ratio by dividing any term by the one right before it. So my ratio is -2/3, and again I showed you the side work. So I did that -4/3 divided by 2, and I did 8/9 divided by -4/3. You want to make sure and grab those signs, because see how those signs are alternating? You want to make sure and work that in to your computations as well. All right, and then it's just a plug and chug, right? A sub 1 over 1 minus r. So just plug and chug here, and we get an infinite sum of 6/5. Okay, so last one's going to be example 9. Or example 8, because apparently I can't count. That should be a 9. Fixed it. All right, so let's find the infinite sum. This one's in summation notation. This is actually easier than some of the other forms it's been in. If you recall, the geometric sequence here has this form of a sub 1 times r to the n minus 1. So looking at this summation and comparing this to this geometric sequence form, we can pretty easily see a sub 1 is 8 and r is 1/3. So boom, a sub 1 is 8, r is 1/3. So plug and chug into our infinite geometric series formula, and we get 8 over 1 minus 1/3, which is 12. Now, just in case you don't know where I'm getting that from, let me just do that on the calculator real quick. So that's going to be 8 divided by 1 minus 1/3. So let's put that in parentheses to tell the calculator that the whole thing is the denominator. So 1 minus 1/3, and we get 12. All right, so that finishes us up for section 13.4.